Aluminium melting furnaces, a dry hearth versus a wet bath. The aluminium industry has many versions of melting furnaces. The simplest and probably most widely used are the single-chamber melting furnaces, a gas-fired reverberatory furnace with metal charged directly into molten aluminium bath, a wet bath melter. A gas-fired reverberatory furnace with metal charge on dry hearth, a dry hearth melter. The efficiency of these furnaces has its limitations, which are related to the physical properties of aluminum, solid, and liquid. Solid aluminium is about 15% more dense than molten aluminium. When melting pure aluminum from solid metal at room temperature to liquid metal at 750 degrees Celsius, from 85 to 90% of the energy is being transferred to the metal whilst it is in a solid form. Liquid aluminium has a thermal conductivity about 50% lower than solid aluminium. In a typical furnace, metal temperature variation from the top to the bottom of the static bath is from 60 to 70 degrees Celsius. A dross layer reduces the heat transfer coefficient of the bath surface. Now, first about a wet bath melter. Solid aluminium charge is placed directly into molten aluminium bath. The advantages of this furnace solution are simplicity, low cost, and versatility. The figure shows solid aluminium submerged beneath the surface of the molten bath. Once submerged, heat transfer to the solid metal can only be indirectly through the surface of the liquid bath. This figure shows the typical performance of the wet bath aluminium melter, where 4,000 kilograms of ingots or scrap with minimal preheat have been charged directly into a molten bath of above 1,000 kilograms. 4 stages can be defined from the operation chart. Stage 1, from 0 to 20 minutes. Initial thermal input to the furnace is very high to recover heat lost from the door opening and because some solid material will remain exposed above the metal line. Bath temperature drops rapidly as the charged material cools the molten metal to a temperature that is close to solidification. Stored latent heat of the molten metal is released as the cooling occurs, and this tends to prevent the bath temperature from dropping below 650 degrees Celsius. Stage 2, from 20 to 35 minutes. Flue temperature and roof temperature rapidly rise to the set point. The bath temperature is maintained at approximately 650 degrees Celsius due to the latent heat of melting aluminium, and the phase change continues to absorb energy from the bath. Thermal input must reduce because the refractory surfaces have reached the operational limit. Heat transfer at this stage is primarily through the surface of the molten metal. Stage 3, from 35 to 50 minutes. Bath temperature increases because the solid metal within the furnace has reduced. Rate of energy transfer through the surface of the bath now exceeds the cooling effect of melting aluminium and casing heat loss. Stage 4, from 50 to 75 minutes. Thermal balance must be maintained, and so the burner system output is reduced accordingly. This last part of the melting cycle delivers the final from 7 to 10% of the total energy to the metal, but requires more than 30% of the cycle time. Heat transfer in this final stage is constrained by the surface coefficient of the molten bath. Now, about a dry hearth melting furnace. This furnace has an extended and elevated charge ramp or sill enables the solid metal to either be preheated or partially melted without coming into contact with the liquid bath. Metal placed on the charge hearth rapidly absorbs energy from the furnace by radiation and convection. Metal remains on the dry hearth until the bath temperature has recovered back to set point. At this time, the preheated and semi-molten charge is pushed into the bath and cold metal is placed onto the dry hearth. The figure A shows the typical performance of the dry hearth aluminium melter, where 4,000 kilograms of ingots or scrap have been charged into a dry hearth of the furnace with a molten bath of about 1,000 kilograms. From the figures A and B, it can be established that average melting rate improved by 25 to 30%, energy consumption reduced by 10 to 15%, furnace utilization is at maximum. The principal reason for the improvement is that approximately from 50 to 70% of the energy is being transferred to the ingots before they are submerged into the molten bath. The total energy required to be absorbed through the bath surface has now been reduced by around 50%. The concept of melting aluminium on a dry hearth offers following benefits. As the solid charge is never submerged under molten metal, the melting rate per unit of area of hearth is much higher than for a wet bath furnace. Solid material can be completely separated from the molten bath, virtually eliminating the risk of a steam explosion caused by wet charge material. Thanks for watching.